Okay, good morning, everyone. It's a great pleasure to have Kawagoe as our speaker today. Kyle did his PhD at University of Chicago with Michael Levin, and now he's a postdoc at University of Maryland. I really like Cal's work, and one of his distinct features of his work is to translate mathematically abstract concepts into very concrete, microscopically defined physical quantities. I think that's really important, really to make this bridge between the math and the physics. And the topic today is also in this direction. Yeah, Cal, please go ahead.
Okay. Yeah. So thank you, Legion, for the generous introduction and also for the invitation to speak. Today I want to tell you about how to compute the anomaly, the anomalies which correspond to anomalous symmetries in 2+1D lattice models. So we'll get into exactly what I mean by that in a moment. And I've made the choice to study, to kind of present today's talk through the lens of looking at 2+1D boundary theories of 3+1 dimensional symmetry protected topological order. You can study these 2+1D theories, anomalous theories in their own right, by just in order to make it a little bit more concrete and to connect this to things people may have heard of. I just wanted to kind of tell the story from an SBT point of view. So with that, let me just go ahead and introduce what is an SPT. So symmetry protected topological phases are gapped phases of matter. Um, so there's a gap between the ground states and the first excited state, even in the thermodynamic limit. And these theories are trivial in some sense. You can continuously deform them to a product state. However, you can't do so without breaking the symmetry or closing the gap. So in that sense, symmetry protected topological phases would be trivial if not for being protected by a symmetry. There's this probably the best known example is topological insulators, and those have been studied for a long time now. Um, okay, so that's our background. Oh, and I guess for those here, if you want to interrupt with the question, I'm fine with it as long as the host is. So okay, so. The boundary theories of SPTs are sort of interesting because SPTs have this sort of holographic kind of principle that if you look at the low energy degrees of freedom of symmetry protected topological phase, that is to say, let's just look at the ground state subspace for an SPT. There's a correspondence between that ground state subspace and the boundary degrees of freedom. So if you fix the boundary, the bulk ground state is sort of completely specified. So this gives you an isomorphism between the bulk low energy Hilbert space and the edge Hilbert space, the boundary Hilbert space. Okay, now this isomorphism is sort of it kind of conserves locality, but only to a point. So that is to say, if you have like a simple tensor, so for example, maybe your symmetry in your SPT is an on-site symmetry, which that'll be the case we're interested in. So it's a simple tensor over all the sites. Um, then what was a simple tensor symmetry or just like a product symmetry in the bulk becomes something that's no longer just a simple tensor. It becomes some finite depth circuit on the boundary. So and when this happens, we say that the boundary symmetry is anomalous. So that is to say, if your on-site symmetry in the bulk becomes a truly on-site symmetry on the boundary under this isomorphism, then the boundary is sort of non-anomalous, if you'd like. And so we're sort of interested in looking at the anomalous case and characterizing that. Um, so another way to say this is if you look at like a 2+1D theory with an anomalous symmetry, you can sort of find a 3+1D SPT to attach it to. So it's the boundary of that theory, where in total the symmetry is non-anomalous. So this is called anomaly inflow, if you want the technical word for it. But okay, so there's a sort of correspondence between bulk SBTs and anomalous boundary theories. So our goal for today is to say, suppose you have an anomalous symmetry action in a 2+1D lattice model. Um, compute the SBT that you can use to sort of cancel the anomaly if you put this 2+1D theory on the boundary of a 3+1D SBT. Okay, and of course that's still a pretty abstract expression, so we'll narrow that in as well. Um, but when someone says compute the anomaly, this is one example of what someone could mean by this. Compute the appropriate SPT phase, which causes this cancellation. So within the cohomological classification of SPTs, if you don't know co group cohomology, that's fine. But the general idea is that there's some function. So say G is your symmetry group. There's some function, omega, which takes in four elements of the symmetry group and spits out a complex phase. So something living in U1. And these different SPTs, at least within the cohomological classification, uh, are completely characterized by this function. So our goal will be to say, suppose you have a 2+1D theory, lattice theory with some anomalous symmetry. We would like to be able to compute this function, omega. And in fact, not just compute in some sense, I guess what I'm really saying is we'll define it. We'll define this function in terms of the symmetry operators in this 2+1D theory. Okay, so and I'm really stressing the dimension we're in because there will be a lot of dimension shifting happening, not in the cohomological sense, but we'll be going back and forth between different dimensions, and I just want to be extra clear. So, so just to reiterate, we're going to be looking at discrete unitary symmetry. So we're not looking at like O2 or something. We're looking at things like, Z4, for instance. And we're only looking at unitary symmetries, no anti-unitary symmetries, at least for this talk. So, okay, our goal is to compute omega, the function omega, that is to say. So we'll just do a warm up. We'll do two warm ups, and we'll start with 0+1D boundary theories. We'll move to 1+1D boundary theories, and then we'll present and those are things that are known, and then we'll present the procedure for computing the anomalies in 2+1D boundary theories. So suppose you have a 1+1D SPT with some left boundary and a right boundary, and you have a symmetry group, let's call it capital G. And this system, because you have a symmetry for the system, it means that your Hilbert space is some representation of the symmetry group. And because of this sort of holographic principle, the action of the symmetry uh, on any ground state, of which there are many, um, is actually sort of imitated by just actions on the boundary. So that is, if I apply UG to a ground state, that's the same thing as applying some operator on the left boundary and some operator on the right boundary, some unitary operator. Okay, so because this is a representation, UG times UH gives the operator UGH. And what this means is that actually this equation, UG times UH is UGH, is satisfied on both the left and right hand sides independently, but only up to a complex phase, owing to the nature of tensor products, of course. Um, so this complex phase means that which you can't always get rid of, quote unquote, by making different choices. This complex phase means that you have a projective representation on the boundary. So whereas you had a linear representation, the boundary representation is now projective. So UG, so if you take this operator, sort of imitating the symmetry action on the left boundary, UGL times HL gives you UGHL up to a complex phase. And that complex phase is a so-called two co-cycle. And you can prove this. So I haven't said what a co-cycle is, but it's a function which takes in this case, two group elements, spits out a phase, and obeys some constraint called the co-cycle condition. And the fact that these operator multiplication is associative implies that this is, in fact, a two co-cycle. So that's just a technical detail that you don't need to understand this talk. But the point is, by just looking at this projective representation on the boundary, you can characterize the anomaly. Okay, so now let's move on to one dimension up. So how do you solve quote unquote solve this problem one dimension up? So that is, we want a procedure that just takes the anomalous boundary symmetry and now we'll spit out a three cocycle or a function of three group elements that is valued in U1. So okay, so we'll play a similar game, but there are some steps before that. So you'll see what I mean. Oh, and I should say this is all in this paper by Elsa Nyack from 11 years ago. Um, Okay, so suppose you have a 2+1D SBT or just a 1+1D boundary theory. So M will be like a disk. M for manifold, say. You have a disk, and then you want to understand you because you have an on-site symmetry on this whole disk, you have sort of a non-on-site symmetry on the boundary. That is to say, you can apply UG to a ground state, and that's the same as applying uh, some other operator called UG boundary M on just the boundary, and those are the same action on the ground states. Okay, or they have the same action on the ground state subspace. So this UG partial M, I just want to move things up to get it out of the way. This UG partial M is some finite depth circuit, if you'd like.
Question.
Yes.
I just want to make sure in the literature, how rigorous do people know that this symmetry localization to the boundary should occur?
Oh, good. So that's a good question. I actually don't know how to prove that exactly. In some sense, it's so I guess I would say one of the sort of axioms of all these topological orders is that uh, if you impose local constraints, there's sort of a unique local state. Which means that the only different ground states you could have could even potentially vary at the boundary. Um, And as far so that's sort of maybe not a great answer because it's sort of by definition these are the things we study. But you could also just say from all the examples you see this just phenomenologically.
Yeah,
Um,
I think maybe this can be more rigorously established by using the property of the mutual information in the system.
mhm,
We proved some properties of the mutual information. I think essentially what we proved is the mutual information decays very fast when the regions we consider are far away. I think that
mm,
may be useful for proving this symmetry localization as some approximation. I think this
mm,
equal sign is just the approximate sign. Uh,
mm.
the error will be bounded by something related to the mutual information.
Yeah, that's almost certainly right. That sounds right to me. I haven't studied it personally. What one thing I do know. So in the beginning of the talk, I said that you have this isomorphism between the ground state subspace and the edge degrees of freedom. That really wasn't entirely true. Really, the because the boundary it depends how you cut out the boundary exactly.
Sure.
It's yeah. So the statement is really which is what you're saying as well. Of course, the statement is really that you can access all the ground states by only applying operators on the boundary. Anyway, I'd love to talk about that at some point. That sounds really interesting.
Mhm.
Um,
Yeah.
yeah,
Thanks.
yeah. So as far, yeah, yeah. So it's great. Thank you for bringing that up. Yeah. So okay. So suppose you now have a 1+1D boundary theory on the boundary of a 2+1D SBT. And let's say, suppose that the action of this symmetry can be imitated by some operator that only lives on the boundary on all the ground states. So now we'll play a similar game to before. So what we'll do is we'll say, well, we're going to quote unquote restrict this symmetry operator, UG boundary of M, to just an interval I on the boundary. So what do I mean by that? If you're familiar with quantum circuits, you can think of this as a truncation of the circuit. But you can also just define it like this. So UGI acts like, and you can formalize this operator algebraically, but let's just use our intuition. It sort of acts like UG boundary of M just in Okay, sorry about that. I don't know why the connection was lost. Let me just share my screen again. Mm, Find. Oh, sorry about that. Here we go. Okay, so we were here, I believe. Okay, so sorry. So let me. I'm not sure why I lost connection, but hopefully it doesn't happen again. Um, okay, so suppose. Oh, right. So because before we had an honest to goodness symmetry representation of our boundary symmetry action. So UG times UH was equal to UGH. So we had that before, but now after restricting the symmetry to just being an interval on the boundary, um, this is only true up to, instead of a phase, some operator. So in this case, because the symmetry acts like the identity outside of the restricted symmetry acts like the identity outside of I, um, uh, and the symmetry acts as the restricted symmetry acts just like the symmetry inside of I. That means that the only difference between UG times UH and UGH must live on the boundary of I itself. So it looks like a representation in I, it looks like a representation outside of I, but near the boundaries, who knows? So, okay, so that gives us there's some operator omega GH, which is supported just on the boundary of I, which makes this equation true. Okay, so using that and associativity, we can derive an interesting relation between these various omega GH operators. So, so just like as the first step, if you combine this UG and UH to create omega GH times UGH, and on the right-hand side, you combine UH UK to get omega HK times UHK sub I. Then you get this equation here. And combining these various symmetry operators and kind of playing this game over and over again, you eventually derive this relation. So associativity implies some relationship between these omega operators. So on the left, you have omega g comma h times omega gh comma k is equal to this g conjugated omega hk times omega g comma hk. Oh, and I should mention this is, of course, from Elson-Nyack. Um, and okay, so now what you can do is you can say, well, you have this constraint, this relationship between these omega operators. Um, Using the fact that omega is only supported on the boundary of I, we also know that this equation sort of must be satisfied by, so take omega L to be, omega is the product of something on the left and right, L and R. This constraint on omega means that omega L also satisfies this constraint on the left side, and omega R satisfies this constraint on the right side, but again, only up to a phase. So that phase is how you get lowercase omega GHK. Okay, so that phase difference is characterized by this uh, oh by this complex phase, and that's what gives you the cocycle. So that is, sorry, to say the cocycle which characterizes the anomaly. Okay, so since we're going to be doing this in one higher dimension, I just want to reiterate what these steps were. And of course, since since I had a technical glitch, it's probably helpful to just go over the steps again anyway. So as a reminder, so for this 2+1D system that has a 1+1D boundary theory, whose symmetry is given by this anomalous symmetry action, UG boundary of M. In order to compute the anomaly or the cocycle, we restrict this boundary operator to an interval on the boundary. And then we say because we started with a representation and we restrict it to an interval, we get that UGIs look like a representation up to some operators on the left and right side of this interval. And then you can use associativity to show that in fact you get some relationship between these omegas. And then restrict looking at how this relationship manifests on the left and right hand side of this interval, you find that it only satisfies it up to some complex phase, which characterizes the anomaly. So it's this cocycle. Okay. So now let's go up one higher dimension. So this is our worst.
Sorry,
Now,
can
oh,
I ask a question?
oh yeah, sure.
So, can you explain again why the omega only sits at the boundary of for the interval I?
Yeah. Yeah. So one way to see this is that so you have to if one's very careful about what one means by symmetry restriction. So what I really mean is that the operator UGI, when conjugating any operator well inside of the interval, is identical to conjugating an operator by UG partial M. And if you conjugate an operator outside of the interval by UGI, you return that operator back again. So that is you're acting like the identity. Now, that means that when you multiply UGH or UG times UH, and then let's say by multiply that by UGH inverse on the right, that operator acts exactly like the identity outside here. And you can show that it must act as the identity, that is by conjugating any operator, will conjugate like it's the identity inside of here. The only operators which are unitary, which have this property, are supported just on L and just on R.
Okay, I see.
Mhm.
Thanks.
Yeah, certainly. Okay, great. Thank you. So, okay, so let's go up one dimension. So we'll play a very similar game. But first, let me outline the geometry of the problem. So suppose you have a 3+1D SPT uh, living on a disk. So that is the three disk, so like a filled in two sphere. Um, there's some symmetry action induced. Uh, so the bulk symmetry action induces an anomalous boundary symmetry action. So that is you have some symmetry action on a sphere now. And within that sphere, we're going to cut out a disk, or rather, we're going to study the symmetry action just on a disk. So we'll restrict our symmetry to acting on that disk. And because we had a representation to begin with on the boundary, this restricted symmetry operators will be a representation again, but only up to some operator on the boundary of the region we restrict to. In this case, this boundary looks like a circle. So it's the boundary of the disk. Then representation up to some operator on the boundary. Oh, okay. Yep, I'm unmuted now. Okay, sorry for the technical difficulties. I'm not sure why I'm losing connection, but
Cal,
uh,
I think you lost the connection when you were at partial M.
great. Thank you. Um, so okay, so we had some so we have some symmetry which we restrict to a disk on this sphere. And because we had a representation, to begin with, the restricted symmetry operators are a representation up to some operator supported on this boundary, so that on this circle. Further restricting those operators now, we'll have some operator on an interval on this circle, which then has some relation based on how we derive it, uh, which is satisfied up to something on the boundary of that interval, which themselves satisfy some relation which we then restrict to a single point and get this phase. Okay, so that's like the big picture before we. Hi, I've switched my network. Can you hear me okay?
Yeah, yeah.
Okay, good. So hopefully it doesn't have issues again because I switched to using my phone as a hotspot. Okay, sorry about that. So oh, let me share my screen. Okay, so all right, so okay, let's start from here. So we have some restricted symmetry operator living on this disk, and then because we started with a representation, UG restricted to the disk times UH restricted to the disk is the same as UGH restricted to the disk up to this operator omega now living on this circular boundary. Now, this operator uh, obeys some constraint via associativity. So we're going to use associativity of these restricted symmetry operators to derive this relationship in the one dimension down. Okay, GH to just being on this interval, which means that we'll have this constraint from before will now induce a new relation. So that is, if omega defined on this circle obeys this equality on the nose, restricting this operator to just a single interval will obey basically the same constraint up to some operator, which now just lives on the boundary of that interval. Okay. So now, this relation then, of course, there will now be a relationship between these different gamma operators. So in particular, if you write the product of omega I, so GH comma K, and GHK comma L in two different ways, which I won't show you how to do because it's really long. But if you express this in two different ways by reducing these products of omegas into gammas, what you arrive at is another relation. So this is okay, so I won't define every term in this, but basically the point is that now instead of having the product of two different omega terms equal to the product of two other omega terms with some conjugation, now you have the product of three different gammas um, uh, is equal to the product of two different gammas with this thing called delta. So I haven't defined delta for you. It's defined in a very similar way as gamma. but I don't want to get into the details just to simplify matters. And there's a bunch of superscripts now, and these pre-superscripts are just conjugating by various elements, like UGM or omega I in different places. So I don't want to get into that either. But the point is that after defining this gamma, which tells you how much this relationship between these omegas breaks, you now can now derive a relationship between these gamma operators. And just as a reminder, these gamma operators live on the boundary, exclusively on the boundary of the interval. So it's the same game as before. So one dimension down, this gamma was just some complex phase, and now it's an operator. So this equality was true up to an operator now. Um, okay, so now what we'll do is we'll say these operators now obey this constraint, and we play the same game. So we'll restrict these operators, which so it's the tensor product of something on A with something on B. And after restricting to just A, we see that this relation gives way to a relation for the operators defined just on A up to some complex phase. And that complex phase is this four cocycle, which we've been looking for.
Cal,
Okay.
can I
Yes.
ask? So, for the case of 1+1D boundaries of a 2+1D SPT, the
Mhm.
crucial equation for the omega to satisfy, I think you call it omega, and that equation
Mhm.
comes from associativity.
Yeah.
And then using the omega, we define the phase, and the phase satisfies the cocycle equation. The fact that it
Mm.
satisfies the cocycle equation essentially comes from some brute force calculation. So it requires some
Mhm.
guess that, right? Can you remind me? I think here the crucial equation is the equation for gamma, is it?
Yeah, that's exactly right. Yeah, so the equation written down for gamma here as a constraint is basically the proof that omega satisfied the cocycle condition before.
And on the previous slide, you had an equation for gamma. Is that coming from associativity or what?
Oh, good, good. So it's not quite associativity. I'm going to call it in a few slides. I'm going to call it pentagonivity.
Uh,
So the idea is the pentagonator is basically if you write this expression in two different ways, the pentagonator gives you a way to relate those two different ways of expressing it,
mhm,
and that's what gamma is.
I see.
Or sorry, this that gives you the relationship between gamma. Sorry. So
Mhm,
gamma is defined as the difference between these two expressions here.
mhm. And another question is, when you do these restrictions, uh, in general, there should be some errors. Just to make sure, do you or do other people know how big the error is?
Oh, the error?
Hmm.
Um, Good. So we're only working in the case where these each of these steps is represented by a finite depth circuit. Um, but so one of the things that makes it difficult to go to 2+1 dimensions is, as opposed to 1+1 dimensions, is that in 1+1 you know that your symmetry is represented by a finite depth circuit, so you can always choose some some let's see restriction. You can always truncate the quantum circuit somewhere, and you can prove that no matter where you truncate it, you get the same cocycle out. Here. When you're restricting to a disk, there's sort of no guarantee that this omega boundary M is going to be a finite depth circuit. So it's unclear if you can actually restrict it as like a truncation of a quantum circuit. Now in our paper, we actually show how to get around this. So it turns out there's an obstruction which is related to the GNVW index of QCAs. And there's always sort of a way to add ancilla to cancel it out. And we show how to compute it and also to cancel it so that you can just so basically turn the problem into one where you can represent omega as a finite depth circuit and restrict. And we show that no matter what restriction you pick, you get the same cocycle.
I see. Hmm. Nice.
So yeah, so there's a lot of there's a lot of technicalities that, in fact, that was the hardest part of the project, probably, was working through that. So,
Mhm. But
but
still,
it's a great point.
yeah,
Mhm.
still in general, I think the boundary symmetry action may not simply be a finite depth quantum circuit. It can be something more,
Mm,
something with a tail, yeah.
yes, absolutely. Yeah, you're 100% correct. So in our paper, we don't address that case. We only address the quantum circuit case.
Mhm.
So that's something new that would be a further direction. That would be really good to explore. We do show, at least at maybe not at a rigorous mathematical level, but at least at a physics level, that even in the case where you have finite tails, if the anomaly is zero, or if our anomaly index is zero, then you don't. Let's see what. I can't remember the exact statement, but basically we deal with the implications of the anomaly calculation giving zero, um, uh, basically showing that certain obstructions vanish, even in the case of tails.
Mhm.
Um, but other than that, we didn't touch that case. So yeah, I'd be really interested to talk to you about it because that's a cool direction to go in.
Mhm. Yeah, thanks.
Yeah, yeah. Okay, great. Yeah, thanks for bringing it up.
Excuse me, I also have a question.
Oh, sure.
Yeah, regarding the pentagonity you just talked about, I'm curious
Mhm.
if it is equivalent to, for example, the pentagon identity of symmetry defect, or are they different things?
Yeah, yeah. So the Pentagon, so what would be the Pentagon identity for symmetry defects? Um, in this dimension is now no longer a Pentagon identity, but a Pentagon relationship. So moving from one way of, if you'd like, parenthesizing an expression to another is no longer equality. It's related by something else. So
Okay,
you can keep going up in these layers. So now, so and I don't know if maybe I'll leave it at that. Does that answer your question partially? I'll actually get into this a little more in a minute.
okay, thank you very much.
Yeah, yeah. So this is part of a broader pattern. So so maybe yeah, rounding up at this spot, it's so what did we do? So we basically we said, okay, you have some symmetry on the boundary, which you restrict to a disk, and now you have something that looks almost like a symmetry representation up to something on the boundary of the disk. That those operators obey some constraint. So then you restrict and you get that constraint is satisfied up to something on the boundary of the interval. Those obey some constraint, and then that constraint is obeyed up to a complex phase. And that's this, you know, cocycle. And of course, one should expect that you can keep going up and up and up in dimension. So, so in some sense, this was the talk I set out to give, but there's one bit at the end I just want to maybe give a hint as to where does this go next in higher dimensions. So for that, we'll need to think sort of from a higher categorical point of view. So if you know what a category is, it's something with objects and arrows between those objects called morphisms. In higher categories, you have arrows going between the morphisms called two morphisms, and arrows going between those called three morphisms, and so on, as far as you'd like. Um, and this is where you get this language of pentagonators and all this. So let's see how this all fits in. So I'm going to do a slight notational change just to match what's in the paper. Instead of calling this disk M, I'm going to call it A. But you still have the interval I and its boundary points A and B. So there's a thing in category theory called a tensorator. So in higher categories, the tensorator, if you'd like, is something that says, now this is kind of maybe an inverse of a tensorator. Um, but the idea is if you know that two things, and this is kind of similar to composition depending on what level of the category you're at. But the idea is that if you have sort of a group and you have, G and H, after restricting to this region A, G times H is only GH up to something. And the general principle in higher category theory is to replace every equality with an isomorphism. So in this case, I'm making sort of an analogy. I'm in some sense, I'm just going to tell you how to read off these various definitions from diagrams. I'm not making any rigorous claim, but I am saying that maybe this higher categorical language gives some intuition for what one should be doing in higher dimensions. So to start with, you say, well, the difference between UG restricted and UH restricted is something called a tensorator that relates it to UG restricted. And associativity gave us an equality which goes across a square. If you'd like, before this, for an honest representation, this is an equality over here, and it's just the interval, which is like a one-dimensional square. Now we have a two-dimensional square, which says that if you recombine GH and K in two different ways, this tensorator relates them. And there's two different ways to do it, and they're the same. So this is a sort of pasting diagram. So if you compose this operator with this one, that's the same as composing this operator with this one. And this story actually goes back, I think, just about a century ago. In fact, some of these equations this equation that was in Elson-Nyack for the 3 co-cycle, of course, it was applied in very different settings for group extensions, but has actually been known for an extremely long time. And in fact, all of this mathematics has kind of a long history that's kind of buried in different patches. So it'd be interesting to see what's actually already known, which I'm not really aware of, at least completely. But okay, fine. So the idea is associativity is represented by this square now. But keeping with our theme of higher categories, you replace every equality whenever you go up at a higher level of a category with an isomorphism. And here, by restricting an operator, what I'm saying is that if you restrict an operator, the identities it satisfied before will now only be satisfied up to some unitary. In other words, some higher morphism, invertible morphism. So that is, after restricting omega to an interval, multiplying this omega by that omega will be the same as this omega times that omega up to some gamma. So what was associativity now becomes an associator morphism, two morphism now. And there's another one, which is the sort of an interchange identity. So if you have an honest, strict 2 category, if you take GH and KL and split GH into G times H, and then split KL into K times L, it doesn't matter which order you do that in, those are the same. But if you have a bicategory, so like a weak 2 category, splitting GH and KL in 2 different orders, those are the same up to something called the interchanger. Okay, so that's what delta represents. So that is if you multiply this operator by this operator, it's equal to this one times this one up to delta. Okay, now delta and gamma satisfy some relationship, which it's non-standard term, but I'm going to call it pentagonivity, which is represented by a cube. So this is a pasting diagram. So in general, if you have a pasting diagram, what it means is you just kind of compose the arrows in the kind of only way they fit together. So that is starting with like a long line on the left going down of one morphisms. You get to this path of one morphisms by applying this 2 morphism. And then you compose it with this 2 morphism to get this path. And you compose it with the last 2 morphism to get this path. And you compare that to composing this 2 morphism with this one with this one. And so we've traversed this edge, which is the same as this edge, to the right edge in 2 different ways. And before symmetry restriction, and at this sort of categorical level, if you'd like, these 2 are equal on the nose. So whereas you have the square representing associativity, this equality is pentagonivity, which again is a non-standard term. But if you restrict gamma and delta, and you sort of say, well, this relationship is no longer equality on the nose, but is only equal up to something in our case, in our dimension we're working in as a complex phase, you get a pentagonator between these 2 halves of a cube. So the fact that this left string of one morphisms is the same on both diagrams as is the right string of both diagrams, you're sort of saying you're gluing these 2 halves of a cube together, and there's a 3 morphism taking you from one half of the cube to the other half of the cube. And now, okay, so this pentagonator is now the quantity of interest for us in the dimension we're working in. And by the way, if you glue together, this is not on the paper, but if you were to glue together these 3 cubes into a 4 cube, at least I guess I haven't checked this very explicitly, but in principle, it should be that if you glued them all into a four cube and looked at the chain of three morphisms going across it, um, as sort of an inequality that gives you the three cocycle or the proof of the invariant on one lower space, the proof of the cocycle condition one lower. And then that then becomes an inequality of this constraint. It then becomes an operator or it becomes a phase, and phases become operators and so on. Okay, so from this point of view, to compute an element of the fifth cohomology group H5, what one should do um, is now build a four cube whose various three faces are built out of things that look like this lowercase omega here, which is now an operator, and you'll have some other things that are kind of higher dimensional versions of interchangers. So you'll have to define some extra types of operators as well and assemble them all into this big four cube whose let's see, whose four morphism going between two halves of the four cube is now the new invariant. So if you didn't follow that last part, that's okay. But the point is, it seems clear to me that you should be able to keep going up in dimension using sort of non-abelian cohomological techniques along with higher category theory. So anyway, but that's at a level of conjecture. I'd be very happy to chat with anyone about this who's curious or if you have any ideas. So just to conclude, um, I showed you a way to compute 2+1 dimensional anomalies in lattice models, or symmetry anomalies in lattice models in this dimension. Um, in particular, computing this sort of de Hoodt anomaly. And as was mentioned in the middle, there's this sort of GNVW index, which is sort of a an obstruction to following our procedure exactly, but there's always a way to sort of cancel out the GNVW index in a canonical way in order to uh, fully extract this four cocycle, and we can compute this two cocycle valued and positive. See how this higher category theoretic formalism fits into higher dimensional systems. So thank you again for the invitation to speak.
Cal, thank you very much for the interesting talk. Any questions? Oh, okay, maybe let me ask a question. So when you do the restriction,
Sure.
do you expect the restriction? So when you do the restriction, there will be a lot of the gamma, omega, delta, all these things coming out. When you do such restrictions, do
Yeah.
you expect, for example, like the equation that defines omega as the difference between different operators U, do you expect this equation is an operator identity, or do you expect it's an identity that holds when it acts on the ground state?
Oh, yeah, yeah. So I guess the general story is anytime you have so whatever was an identity in the last dimension now becomes after restriction, of course, is a phase, but in the next dimension up there'll be some unitary operator which relates these two expressions instead of an identity or a phase. I don't know. Maybe I didn't understand your question, but
Can we go back to some of the
oh
previous
yeah,
ones?
sure.
Maybe just the one
Uh,
that defines capital omega. Yeah,
yeah.
the one before. Uh,
This
Maybe the one yeah. For example, this one is also fine. This one is this equation an operator
okay.
identity or identity that holds when both sides act on the ground state?
Oh, good, good. Yeah, yeah. So at this point we're working on the boundary theory. So in some sense we're only working in the ground state subspace. Um, so as an identity, this is true as operators within the ground state subspace. Uh, Generically speaking, I don't have an argument that these operators, let's see, they're representatives in the full bulk theory. I don't have an argument this is true in the full Hilbert space. Although I would expect in examples for it to be the case that this is an operator identity on the nose. Just because one lower dimension that seems to be the case, but
Yeah,
I
yeah.
haven't investigated
Yeah, in
this.
1+1D, this kind of identity is just an operator identity.
Hmm.
Yeah, you mean in high dimensions,
Yeah,
you would expect it to be an operator identity?
I expect it to be an operator identity as well. And in particular, it's the space is like highly degenerate, so it's some like gapless ground state subspace. So it's some big space in which like these operators are living, um,
Sorry,
instead of just being like true on a thing.
I think the connection was a bit bad just now.
Oh,
Say
sorry.
you do not expect it to be an operator identity.
No, I guess I would expect that in any example, like any exactly solvable example, this would be an operator identity. I couldn't prove to you that in any conceivable example that it must be operator identity, but
Uh,
in general, I would expect it to be.
I see. And if we keep going down, besides this
Mm.
omega, there's also the gamma,
Mm.
like this one. Do we also expect this one to be an operator identity?
Yes. Mhm.
Uh-huh.
Yeah.
So I see. So in other words, the anomaly extracted here is purely a property of the symmetry action itself. It has nothing to do with, it doesn't refer to any state or Hamiltonian.
Yeah. Yeah, that is correct. Yeah.
Mhm.
Yeah. And in fact, so maybe I'll use your question to say another thing. That this whole story is really related to various types of group extensions and non-abelian cohomology. So in some sense, if you want to understand a group extension, what you're really saying is you'd like to know how you're looking at how H maps back into G via some representatives, and you're looking at the difference between the group law in H won't look like the group law in G. It'll look like the group law in G up to something in the kernel of that map. And that's really this else-Nyack story is the thing in the kernel of that map is this omega. But of course, you can play this game with sort of longer group extensions, longer chains. And now every step of the way, so whereas in 0+1, you're sort of saying you have a projective symmetry. One dimension up, you're saying, well, you have a representation up to operators, but at the next level it becomes phases again. And you say you have a representation up to operators, which obey some constraint up to operators, which then one level above is phases.
Mhm.
Um, so this is something studied in non-abelian cohomology, but I'll admit I haven't. I've tried to read a lot of the literature, but it's there's a lot out there. So there's some more connections to be made between this math and
Mhm.
this field in physics.
Mhm. Yeah, thank you. Other questions?
Yeah.
Yeah, hi. I still have some questions, maybe related to
Sure.
the pentagnet. So first of all,
Hmm.
may I ask if we can talk about symmetry defect at this level? I mean, in
Hmm.
we don't talk about states or Hamiltonians, but purely about symmetry. Can we talk about symmetry defect?
Oh yeah, certainly. Yeah. So it's not been done in this dimension, but one example is if you look at another work of mine about symmetry-enriched topological order in 2+1 dimensions. More or less the thing that we're doing for symmetry defects, symmetry protected order as well. So you take defects extending into the bulk, and then you try to compose those in sort of operator order, if you'd like, and looking at how you have a difference between two ways of composing these operators, and you have some bulk symmetry defect version of this story in one dimension down.
I see. Um, then I'm still curious if this pentagnator, how is this pentagnator related to the symmetry defect on the 2+1 dimensional boundary? I mean, on the
Mm,
two plus one dimension boundary, it seems that you can have some symmetry
mm.
defects that have pentagon identity. Then,
Yeah.
and is this pentagnator related to that, or they are different things?
Yeah, absolutely. So actually, this is a work that's not published yet. But Michael Levin, Wilbur Shirley, and I are there's basically a way to move. If you think of a way to like move domain walls in a very careful way
Yeah,
that
yeah.
uh, imitates one way of doing associativity versus another way, and they're related by a pentagonator, which is this phase. So we,
Oh,
we
I see.
are working on that. Mhm.
Oh, I see. So basically, this pentagonator is somehow, maybe I should say, the same thing as the pentagon identity on the boundary.
Yeah, that's right. Yeah, so if you look at the Pentagon identity, uh, if you arrange the symmetry defects or just domain walls in that
Okay.
configuration, or another way, the difference between those two ways of doing it will be the pentagonator or the H4 element.
Oh, I see. Thank you. And that maybe that's why you are calling it pentagonator, although it looks like a hexagon. Is it? Is it the reason?
Yeah, that's right. So the secret is that in the Pentagon equation, the delta looks like the identity, um, and
Ah,
so then you only have it's like a cube with one side contracted.
I see.
The interchanger is actually a very subtle piece of information that, in some sense, you always want to treat it as trivial. So, uh, yeah,
I see. Thank you very much.
yeah. Thank you for the question. And of course, I'm also happy. Whoever wants to chat, just feel free to email me. Um,
Cool.
Mhm.
Thank you very much.
Any further questions? Okay, if not, let's thank Kyle again for a very interesting talk. Thank you, Kyle.
Yeah, and thank you very much for the invitation. I appreciate it.
Yeah. See you.
Okay. All right. See you.